This video is about atmospheric pressure and winds, which are two essential elements to understanding weather and climate. The atmosphere is made up of gases, and gases are always in motion. That's what it means to be a gas, is that molecules are always moving around from point A to point B. When they move, they put pressure on their surroundings. For example, we know that from our everyday lives. If you see a pot and the gases inside are getting very hot, they can throw the lid off the pot. When this tire popped, the gases inside came flying out. That's because we have higher pressure in lower pressure areas, and air always moves from higher to lower pressure. You pump up the tire, it's under high pressure. You put a hole in the tire, it wants to come out to a lower pressure area. We see the reverse on the left. You see a bottle that was sealed at the top of a mountain at 13,000 feet. It's very low pressure up there because the air is very thin. Then somebody carried that bottle to the bottom of the mountain where it was 1,000 feet, and the new high pressure around the bottle that was much higher than the original low pressure at the top crushed the bottle from the outside in. So gases are always in motion, and adding heat always increases that motion. Heat makes air expand, and in the atmosphere that can mean outward or upward. But gravity pulls air downward. So there's this tug of war between air wanting to expand upwards with heat and then gravity pulling it down. So when you see air high up in the atmosphere, that means either some heat or some other force must have allowed it to get up that high. Most of the air is down towards the surface of the earth because gravity pulled it down there. Because air expands with heat, warmer air will become less dense. There's simply fewer molecules per square inch. Same thing is true in reverse. When air gets colder, it contracts. There are more air molecules per square inch. Warmer air expands more, so it tends to rise and it's less dense. Cooler air tends to sink, it's heavier, and it's more dense. Air pressure in millibars usually hovers somewhere within 100 of 1,000 millibars. So on this barometer, you can see the millibars around the outside don't go below 960 or so or above 1060 or so. The inside of the barometer has different units. You can also see that different types of weather are associated with different pressure. That's because moisture, like clouds, only gets into air on a space available basis. By that I mean that air always has first place and water molecules always have second place. So water molecules only can get in between the air molecules when those air molecules are spread out far enough and the water can get in the cracks sort of between them. But if you have high pressure air that's very dense, there's no longer a lot of space between those air molecules. There's nowhere for the water molecules to get in there. And so it's clear skies. And you can see that in the picture. Notice that as the pressure gets higher, they have clear skies. They have the sun out, there's no clouds. Whereas the lower and lower the pressure gets, the more expanded the air is, the more space between the molecules, the more that allows humidity to get in between the air molecules. And so you see cloudy, rainy day at low pressure. Weather maps often show air pressure in millibars, and we see on this the highs and the lows. H's are the highs, L's are the lows. It's similar to a topographic map where they show mountain peaks, the highest elevations around. It's the same thing, except it's the highest barometric pressures around that neighborhood. And these are iso lines, specifically isobars, lines of equal air pressure. So for example, anywhere along this line is 1,008 millibars. Anywhere along this line is 1,004 millibars. And you can see how these pressures are ascending 1,000, 1,004, 1,008, up to a ridge, sort of like an elevation, like the top of a roof or the ridge of a mountain. It's the same thing, except this is the highest line of pressure around, a pressure ridge. By contrast, these pressures here and here are descending downward, sort of like a valley, into a trough, the lowest line of pressure around. And we still have our highs and lows, our peak pressure and our lowest pressure on the map. So as we said, in the big picture, one of the main themes to remember in this whole section is that air pressure wants to even out and create an equilibrium across space. So if there's a higher pressure area here and a lower pressure area here, the higher pressure air will move towards the lower pressure to add pressure there and even it out across the land. So wind is simply the motion of air from higher pressure to lower pressure areas. That's what wind is. It's the evening out of air pressure across the land. So there's a useful phrase we can get a lot of mileage out of. Winds blow from highs to lows. If you can remember that, that will come in handy a lot. Wind blows from highs to lows. And by that, it means pressure. You can see that on these diagrams. On the left and the right, it's showing the same thing, just from two different angles, from a bird's eye view on the left and then a side view on the right. On the left, you see a high pressure area above 1020 millibars. And the blue line is the wind traveling down to a lower pressure. Wind blows from high to low. On the right, you see the same thing, a higher pressure area on the left and the wind blowing towards the low pressure area. Because again, nature wants to even out the air pressure across space. So another way of looking at it is, if we know winds blow from highs to lows, then whenever you see an H on a map, you know that winds are blowing out of that high in all directions, like a pump sending winds out in all directions. And if you see a low on a map, you see that it's like a vacuum. Winds are coming in from all directions. Winds blow out of highs, winds blow into lows, like a funnel. For example, the eye of a hurricane is an extremely low low, so all the winds around it are attracted into the low. In the big picture, wind is the largest and fastest redistributor of temperature and moisture across the globe. And by that we mean, if you recall, we said the sun creates three major climate zones in the world because there's the most insolation around the tropics. We call that the tropical or torrid zones. It's the hottest zones in the world, the most energy from the sun. The mid-latitudes receive moderate insolation. They're the temperate zones. And then the polar regions are the frigid zones, or coldest zones of all. But those temperatures that start there don't always stay there. Wind can move them around and redistribute them around the globe. Ocean currents can do the same thing. So winds can take hot temperatures from the tropics and ocean currents as well, and they can move those hot temperatures out towards the mid-latitudes when tropical air masses move to the north. In the same way, winds and ocean currents can take cold temperatures from the North Pole regions. Then it can take those polar air masses and bring them south into the mid-latitudes. So living in the mid-latitudes like the United States, Europe, China, you get both polar and tropical air masses moving to you through winds and ocean currents. So you can think of the winds and the ocean currents as hands that nature uses to move temperatures and moisture around the globe. Winds can be local or global. Local winds move shorter distances, whereas global winds move in long belts around the globe. Local winds can also move in any direction, whereas global winds tend to be more predictable because they follow the patterns of highs and lows created by the sun. Local winds are also closer to the Earth's surface, whereas global winds are higher up in the atmosphere. And local winds are less predictable because they respond to local changes that create uneven air pressures. For example, just from day to night, the air pressures change in local areas, especially if you're near the ocean or up in the mountains or in a valley. We need to pay special attention to this next point because it's often confused or forgotten and can mess you up on a test. We name winds for the direction that they blow from, not to. I put this picture, The Birth of Venus by Botticelli, because it illustrates the point. In the myth, Venus was born on the ocean and was blown to shore on a shell by the west wind, whose name is Zephyr. You see him in the picture and off on the left. But if you look carefully at the picture, Zephyr is not named the west wind because he's blowing to the west. He's named the west wind because he's blowing from the west. So now that we know that winds blow from high to low pressure, we can give a name to that difference between high and low pressure. It's called the pressure gradient. Gradient is a word used for any type of difference between two sides. For example, I remember using Adobe Photoshop software. And there's a tool you can use called the gradient tool. You have two colors on either side. Let's say one is gray and one is white. And you use the gradient tool and you drag it across, and it gives you a line or a shape that starts out gray and it gradually transitions to white. It's the same thing here, except it's a pressure gradient. There's high pressure over here on the left, and there's a gradual transition where the pressure gets lower and lower and lower to the right. Winds always go down the pressure gradient. That's very important to remember. They always blow from higher pressure down to a lower pressure. The global winds in this picture look very complex, but at their essence, what drives them is simply the pressure gradient. And the biggest pressure gradient of all is between the equator, where the lowest pressure is, and the polar areas where the highest pressure is. So the basic pressure gradient driving the global winds is from the polar highs down to the equatorial lows. So overall, there are three forces which make the wind blow. The wind is driven by the pressure gradient. But after it gets that direction from the pressure gradient, down the gradient from highest to lows, then it will turn due to the Coriolis effect. It makes winds appear to turn when they travel long distances. And then there's the force of friction, which slows down the winds, depending on what's on the landscape. Let's look at the Coriolis effect. The Coriolis effect causes long-range, long-distance flying objects, like a wind, like a missile, to appear to turn because the Earth is actually turning underneath it as it flies. And that apparent turn is always to the right in the northern hemisphere, as you see in the diagrams, and to the left in the southern hemisphere. If you take a close look at the northern hemisphere, you can see no matter which way the wind starts in the dotted lines, it always turns to the right. It starts out going west and it turns to the right, starts out going east, turns to the right, starts out going south, turns to the right. Any way it goes, always turns to the right in the northern hemisphere. In the southern hemisphere, you see the opposite. No matter which way it starts, it always turns to the left. One of the keys that we'll see in a moment is that at the equator is the only place where there is no Coriolis effect. So what's causing the Coriolis effect is what's known as the Coriolis force. It's acting always at 90 degrees to whatever the direction of the wind or missile is, but more and more and more as you go higher and higher latitudes toward the poles, and no effect at the equator. Well, let's think about why that is. Let's look at two examples. Back when I was growing up in the 1980s, it was the Cold War, and the US and Russia each were working on intercontinental ballistic missiles, like the one on the bottom left. These are missiles that you can shoot from one country and end up hitting another country thousands of miles away. Those missiles would have to travel for hours up in the sky. So, for example, if you were in Moscow and you wanted to fire one of those missiles and hit the Pentagon in the United States, or by contrast, if you were in the United States and you wanted to fire a missile and hit Moscow, you'd have to think, where am I going to aim the missile? Would you aim the missile at wherever Moscow was at that moment that you fired it? Or if you're in Russia, would you aim it at the Pentagon, wherever the Pentagon was at the moment that you fired the missile? Before we answer that, I'll give you another example. Imagine you had a special superpower where you could throw a football for thousands of miles and hit a target. So you're in the United States and you want to try to hit a Pacific island, you pick Hawaii. If you throw the ball, say, from Virginia, thousands of miles, can you simply aim at wherever Hawaii is at the moment that you throw the ball and expect that ball to end up hitting Hawaii, let's say 5 hours later when it lands? So the answer to those questions is no. When you aim directly at the target, but the target is thousands of miles away, and the football or the missile has to travel those thousands of miles for many hours, let's say 5 hours to get to the target, then by the time the missile or the football arrives, the target will have moved. Because remember, we said the Earth spins 15 degrees of longitude every hour. So you actually have to aim at wherever that target will be in 5 hours because of the Earth's spin. And if we were to make a map of the path of the football or the path of the missile, it would actually look like the football was turning to the right the whole time. Not because the football actually turned itself, but because the Earth spun 75 degrees in those 5 hours underneath it. Another way to think of this is that the maps that we draw are always drawn from our own perspective, but we're standing on the ground, and that ground is actually spinning through space, 360 degrees of longitude every day. But it's very difficult to show that unless you have some animation. So actually, it's the backdrop, the Earth's surface that's spinning, even though it looks like the wind or the missile is spinning as it flies above the Earth. So to visualize the Coriolis effect and why it increases as latitude increases, we can think about how the Earth spins. The Earth has an axis, and all of the latitudes we know are parallel, so they all follow the same plane of rotation around the Earth. No matter where you are, what latitude, you're always rotating on the same plane, which is perpendicular to the axis. Sort of like a carousel goes around a merry-go-round with that pole in the middle. The pole is the axis, and you're spinning around on some latitude. And we could think, if you are along the equator and you're flying above it like a wind or an airplane, then what are you going to see below you? Will the Earth be spinning around like a carousel circularly? Well, not really, because you're going to actually be on the surface where the surface of the Earth is actually going to be perpendicular to the plane of the Earth's rotation. So all you're going to see is the equator sort of going by you from west to east in one direction. You're just going to see flying above the equator coming in from the west and moving to the east in one direction. But one direction is not really a spin from your perspective. So the Earth is not really twisting underneath of you from your perspective. But as you go further and further up the globe, then you are no longer just perpendicular to the plane of the Earth's rotation. You are more and more at an angle because the surface of the Earth, with the curvature of the Earth, gets more and more and more to where it's at the end, at the poles. At the poles, you're actually parallel to the plane of the Earth's rotation. So let's take the opposite example. Let's go up to, for example, if you're just a few steps off the North Pole, right, or at the North Pole, then if you're a wind flying above the North Pole, then the Earth's rotation is literally rotating underneath you 360 degrees. It's as if you're looking down on the merry-go-round with the pole in the middle, and the horses around the outside are all spinning around and around and around in a circle. So that's why the Coriolis effect gets so tight the further and the further you go up, to where if you were a plane flying in a single straight line just really close to the North Pole, it would literally look like you're flying in circles. And everywhere between the equator and the North Pole or the South Pole, the Coriolis effect just gets bigger and bigger and bigger as the angle of the Earth's surface becomes more and more and more parallel instead of perpendicular to the plane of the Earth's rotation. And therefore, you can have the Earth rotating underneath of you more and more and more. Because the Coriolis effect gets smaller and smaller as you go towards the equator, that's the reason why so many countries have space bases around the tropics. For example, US, they have Cape Canaveral, and France operates a space base in French Guiana, which is actually part of France. People from French Guiana have a French passport. It's an overseas department. And that space base is actually part of the European Space Agency, ESA. It's called the European Spaceport. But as we've said, the only reason you see all these turns on this map of global winds, turn, is all because of the Coriolis effect. This map looks very complex, but once we see the patterns, it'll be much more simple. The Coriolis effect is also the reason why hurricane winds spin. They are long-distance winds which travel for hundreds of miles. So now that we talked about pressure and winds, we can talk about air masses in fronts, which are essential to understanding the weather. An air mass is simply a giant region of air that has a similar moisture and temperature throughout, a uniform common temperature and moisture. For example, if you look on this map, all these giant blobs are air masses. In the middle, you see a continental polar air mass, CP. It is cold because it's polar, it's up in the higher latitudes, and it's dry because it's in the continental region, which means far from the ocean. By contrast, off to the left, you see a maritime polar air mass. It's also polar, so it's cold, but it's also wet because it's over the ocean. So the latitude tends to give it the temperature, and then continental versus maritime tends to determine whether it's wet or dry. You have maritime tropical at the bottom, and then continental tropical in the middle in the yellow. So with all these air masses, they bump into each other, and there's always an edge or surface at that point where they touch. That's very important. It's called the front, a weather front, the surface or edge where differing air masses with different temperatures and pressures meet. You can see in this picture all these white fronts between the air masses where they meet. The term fronts was originally given because of the similarity between two air masses meeting along a surface or edge to two armies meeting on a battlefield, because they were named right about the time of World War I by a Norwegian meteorologist who noticed the similarities between war maps and weather maps. On the left, you see a map of World War I with this, for example, brown line, which is a front at 1917, and other war fronts between armies. And on the right, you can see sort of a modern day front of sorts. In football, we have the line between two teams. These are places where two masses meet. So on a weather map, you have fronts between air masses. So here we have colder air, and then a different type of air, warmer air over here. Have to be different, colder and warmer. And the line between them here is the front. Again, you have warmer air, and again, different type of air, cool air over here. And there's a front between them. These are all air masses. So on this map, we have 1, 2, 3 air masses, cool, cold, and warm, and they're all meeting each other in two fronts. The symbols along the line, like the triangles or the semicircles, tell you in which direction the front is moving. So this cold front here is moving to the southeast, and this warm front is moving to the northeast. Before we get into how the fronts actually work, in the big picture, they're sort of similar in that in either case, whether it's a warm front or a cold front, you're going to get the warm air to rise. And when it rises, it's going to cool off because it's using its heat to rise. And when it cools off, it will have to condense. Any moisture in it will condense. You'll get clouds and usually some type of precipitation. So the cold fronts or the warm fronts are where the rains are, where the snow is. But the difference is a cold front operates much faster and the storms are much more intense. A warm front operates much slower and the storms are much more light, like drizzle. The names of fronts can be confusing because when you look at the pictures, they both have cold and warm air. So how do we know if it's a cold front or a warm front? And the answer is basically it's just whichever air ends up replacing the other. So imagine you're a person standing here along this front, right on the edge between cold and warm. If it's colder at the end than when it started, that was a cold front, right? On the right, if you're standing here on this edge between warm and cold, somewhere in here, if it gets warmer in the end than it was before, that's a warm front. So it's whichever air mass takes over the other one, sort of invades the area. So to go back to our battlefield analogy, if we have two armies that meet along a front, whichever army is still standing in the end, that's the one that you name the front for. So let's look up close and see how a cold front works and then how a warm front works. They're quite different. Remember that cold air is denser, it's heavier. So if it has momentum, and you see on the bottom, if you follow the diagram, it's coming in and moving in towards the warm air. That colder air is much heavier than warm air. So it's going to easily bulldoze underneath the warm air, sort of shovel it up, dig it up, and throw it up into the sky, like you see the arrows in red. And this all happens fast. So if you're outside amid a cold front, you will see the temperature drop. And then within 15 minutes, 20 minutes, 30 minutes, you will see rain showers come down. So cold fronts happen fast. They give you your bigger storms like this: heavy rains, heavy snow. So if cold fronts are fast and create heavy precipitation, what about a warm front? A warm front works a very different way. If you follow the picture, here's warm air with momentum, and the arrows are moving toward the cold air. But unlike the cold front, this warm air cannot simply dig underneath the cold air and bulldoze it out of the way because it's much lighter than the cold, denser air. But what it can do is simply bump into the cold air as if you bumped into a house, and it crawls up the side very slowly. So here comes the warm air from the side. It hits colder air. It can't go into it. So it simply kind of like rises up the side of it, up to the top. And it's as if it gets up on the roof of that house. You can see the warm air here sort of wafting its way up over the cold air, just climbing on top of it. But what the warm air can do is slowly sort of climb up the side of the cold air. So the cold air just stays there, and the warm air slowly slides up the side because it can rise, it expands, it's warm. And this takes a long time. So if you're standing along a warm front, you're not going to notice it for a long time because you're still going to be standing in the cooler air because the warm air is really overtaking it from above where you're standing, way up in the sky. And what happens here is that eventually, as that warm air accumulates on top of the cold air, you get what they call a vertical front. So you have warm air on top of cold air. Instead of warm air here on the side and cold air here, it's warm air up here and cold air down there. And the warm air will slowly warm up this cold air from the top down, little by little, until finally there's nothing left but warm air in the whole area. That all takes a long time, and all that while, the warm air is slowly condensing along that vertical front, right along that edge where the warm air is meeting the cold underneath. Along the edge between them, the warm air is condensing as it gets cooled off, and little bits of rain are falling down as it does. And that's drizzle, light rain, like this. So to sum it up, in a cold front or a warm front, you get precipitation. But the cold fronts happen fast and they have heavy precipitation. The warm fronts happen slow and they have light precipitation. You can actually have snow from a warm front, but it'll be the type of snow that's very light and can easily change to rain. Finally, let's look at occluded fronts. The word occluded means blocked, shut down. So if you look on the picture on the right, you see there's 3 air masses instead of 2. We have a front here, the blue cold front, where you have a cold air mass 3, and a warm air mass 2. That's a front in progress. But then you have a second front, this red one over here, between air mass 2 and air mass 1, warmer and cooler. That's a warm front. So you have a cold front and then a warm front. But we know that cold fronts happen fast, they move fast. Warm fronts move slow. So therefore, we know this cold front is going to easily catch this warm front. And when that happens, that cold air in the cold front will bulldoze both of the air masses. It'll bulldoze not only the warm air, but the cooler air over here too. So this air mass and this air mass, number 2 and number 1, will both be bulldozed by number 3. You can see that in the picture on the left. Air mass 2 and air mass 1 had a front there. That was the warm front. But air mass 3 is even colder than both of those. So it's coming in and bulldozing air mass 2, and it's about to bulldoze air mass 1 too. But what it's doing is the edge between air mass 2 and air mass 1 right here, this surface, that used to be on the ground, but now it's being lifted up. See how the edge between air mass 2 and 1 is no longer touching the ground? That means it's ending, it's stopping. So that right there is what you see in this purple up top, where it says occluded front. It's catching it. Okay, so when the cold front is catching the warm front, it stops this front and ends it. That's the purple. It's already ended up there. It's already been blocked. And it's about to block the rest of it down here. And that's going to turn purple too. And in the end, after a lot of precipitation, there'll be no more fronts because air mass 3 will have bulldozed and dug underneath both air mass 2, lifted that up, and lifted up air mass 1, and there'll be only one air mass left. So now that we understand all these mechanics of pressure and winds, the Coriolis effect, air masses and fronts, we can start to look at the global wind systems that we're going to be talking about in the future. The diagram looks very complex, but we know that winds blow from highs to lows. And sure enough, anywhere where you look in this picture, you see that happening. Look at the top. The polar high is blowing toward the polar low. See, all these arrows are blowing out toward this 60 degrees polar low. Look at the equator and look at 30 degrees. The subtropical highs around 30 degrees are blowing toward the equatorial low. Winds blow from highs to lows. And sure enough, again, the subtropical highs are blowing this way, again toward the subpolar low. So everywhere in this picture, we see winds blowing from highs to lows. So that rule helps us a lot. Then we said that winds turn due to the Coriolis effect. They turn to the right in the northern hemisphere. And look, there they go, turning to the right everywhere you look in the northern hemisphere and to the left in the southern hemisphere. That explains the turns. And then we said there are weather fronts where two masses collide. And sure enough, we see that in this picture. We have the polar front right here. It's where this air mass meets this air mass along this line. This is where our blizzards are in North America in the winter. And finally, there's another possibility where two air masses don't collide, but simply converge. They go in the same direction instead of running into each other in opposite directions. And that convergence zone is right here. You see these winds and these winds essentially travel into the same road, so to speak, together. And this is called the intertropical convergence zone. We'll be talking more about it later. So that's a look at atmospheric pressure and winds. These are essentials to understanding global climates, and they're going to be very useful to us as we go forward.